In this video, we're going to look at several examples of ionic compounds on the worksheet, Another Formula Review. In this worksheet, all of these substances, these names, are dealing with an ionic compound. So that means that they're dealing with a metal that's on this side of the periodic table and a nonmetal that's on this side. On our oxidation state chart that I've been using for the videos, I have it labeled the metals on this side, which are going to lose electrons. They have a low electronegativity value. Sticking together with, connecting with, bonding with a nonmetal on this side of the periodic table. We like to call this the stair-step line, and nonmetals on this side. So when we look at our chemical bond chart, the type of compound that we're dealing with is an ionic compound, and the bond's name is the same, ionic. When we move over here, the compound name and the bond name will be different from one another. In this category of ionic bonds, we're looking for a metal atom and a nonmetal atom. And the important thing is that the electronegativity difference, the attraction of electrons, and I think that's on the back side of this page, the electronegativity value, the attraction of electrons. Metals have a low attraction, nonmetals have a high attraction. What that means is the difference between the two values is big. Because the difference is big, the metal is strong enough to take, the nonmetal is strong enough to take the metal's valence electrons away. So there is a transfer of electrons. It creates or produces what is called an ionic crystal structure, where we get a metal with two, in this case, a metal with two nonmetals, a metal with two nonmetals. Sometimes it can just be 1-to-1 ratio, sometimes a 1-to-3 or a 3-to-1. But now they're no longer atoms anymore. They are now ions, so we call it an ionic crystal, a repeating pattern of positive and negative ions. The smallest unit that repeats itself is called a formula unit, and the way we represent the bonding is through the valence electrons leaving the metal, going over to the nonmetal until the metal has a complete outer energy level and the nonmetal has a complete outer energy level. The metal becomes positive, the nonmetal becomes negative, and we can come up with the formula. This page is dealing with the name to the formula for ionic compounds, because every one of these has a metal with a nonmetal. So let's look at a couple of examples of a metal with a nonmetal. Let's take a look at number 10, potassium nitride. Potassium is in column 1A. Because it's in column 1A, potassium would be a K with a plus. Nitride, notice that it ends in IDE, so that means it's from nitrogen, the periodic table. It's in column 5A. That means it's going to try to gain 3 electrons, so an N with a 3 minus. A 3 minus and a 1 plus do not match. We need 2 more 1 pluses. So now we got 3 Ks with 1 N, K3N. If we look at another example, number 23, calcium bromide. Calcium is in column 2A, so it's a 2 plus charge. Bromide is in column 7A, so it's a 1 minus. Notice the bromide, IDE, must have come from the periodic table. So it's a Br with a 1 minus. The 2 plus and the 1 minus don't cancel, so we put another Br minus, and we end up with 1 Ca and 2 Brs. We always put these together so that the charges cancel out. This is what we would consider a standard ionic compound. Now, if we want to go to one that includes a polyatomic ion, let's look at question number 15. Aluminum chlorate. Aluminum comes from the periodic table in column 3A, so it's a 3 plus. And then chlorate, we notice that it ends in ATE, so we're going to have to look it up on the back side of the periodic table. Chlorate is ClO3 with a 1 minus. So it's 1 Cl, 3 O's, and there's a 1 minus charge. That 1 minus is a superscript that refers to the charge. The 3 is a subscript that refers to 3 O's. So this is not a 3 minus. It's a 1 minus. You need a ClO3 with another 1 minus and another ClO3 with another 1 minus. So you have 1 Al and 3 ClO3s. When you have more than one polyatomic ion, you have to put it in parentheses. And then there are 3 of them, so you put a 3 on the outside. If we look up here, question 26, AlOH3. Now, when we look up Al, it's a 3 plus charge. Al is a 3 plus. And this grouping we need to recognize is a polyatomic ion. It's OH. And its name is hydroxide, and it's an OH with a 1 minus. So it's going to take 3 OH groups. This is why they wrote OH in parentheses with a 3 on the outside. So its name is simply aluminum hydroxide. This reminds us that there are 3 on the polyatomic ion chart that ends in IDE, peroxide, hydroxide, and cyanide, that didn't come from the periodic table. Remember, all of these that changed their name changed them to IDE, but these with the ending of IDE are on the polyatomic ion chart. I wish they would have used a different ending for those names, but they chose IDE. Then let's take a look at a transition metal that can have multiple charges. When we look at nickel on our oxidation state chart, you will notice that nickel can be a 2 plus or a 3 plus. And in this case, apparently, according to this, it can also be a 4 plus. So we will trust this and go with the 4 plus. According to our chart, this would be written incorrectly because the only options are a 2 plus and a 4 plus. Phosphate, PO4 3-. The subscript refers to 4 O's. The superscript refers to the 3-. So now, now we need to 6- and I with a 4 plus, 8 plus, and now PO4 3-, 9-, we need another plus, 12 plus, and finally 12-. So it took 3 NIs, Ni3, and 4 PO4s, so I got to put PO4 in parentheses, and then a 4 on the outside. Transition metals. Let's take a look at Ag. When we look up Ag, Ag is in the transition metal section. But notice when we look him up on the oxidation state chart, Ag can only be a 1 plus. Because of that, we do not have to figure out what it is. Ag is a 1 plus, Cl is a 1 minus from column 7A. So it's just simply silver chloride. So although Ag is in the transition metal section, because it does not have multiple charges that it can be, we do not include a Roman numeral. But let's take a look at Zr. Zr, zirconium, is in the transition metal section, and it is here. Now, of course, I picked another one that does not have multiple charges. It can only be a 4+, and SO4 is a 2-. It's a polyatomic ion that's listed on the back side of your periodic table as an SO4, 4 O's for the subscript, a 2- charge. So you're going to need 2 SO4s. That's why it's zirconium sulfate with an SO4 with a 2-. Whoop, I put zinc, it's zirconium. Zirconium sulfate. No Roman numeral because it does not have multiple charges. Now let's pick one that does have multiple charges, such as SN. When we look up SN, SN can be a 2+ or a 4+. So that means we have to figure out what it is. So we write SN, but we don't write its charge because we don't know yet. Now we look up NO2. Nitrite is NO2 with a 1-. Nitrite, NO2, 1-. And there are 3 NO2s from the formula. 1-, 1-, 1-. That means the SN must be a 3+. And according to this chart, 3+ is not even an option for it. So maybe it is an option if you look up SN on Google, but in this case it's not, but we will go with it for the sake of this worksheet. So SN is 10, so it's TIN with a Roman numeral 3 and then nitrite. For our test, we will only have options of ions that are listed on this oxidation state chart. I hope this helps with understanding names to formulas as well as formulas to names for the 3 types of ionic compounds, what we would call the standard ionic compound, one with polyatomic ions, and ones with transition metals.